Our next presenter is going to be Jenna Adams, Dr. Jenna Adams. She earned her PhD in geochemistry from the University of California, Santa Barbara, and subsequently completed the postdoc research position at the Colorado School of Mines. She then joined Haley and Aldrich as a geochemist, where she has been consulting in the mining and energy sectors for the past 2 years. With over 9 years of experience in geochem modeling, computer programming, Jenna's professional work primarily involves applying analytical, geochemical, and statistical models to characterize mine-related materials, study water-rock interactions, and assess contaminant fate in transport in soils, groundwater, and surface water across diverse geologic settings. Her presentation is going to be Guiding Mine Closure, a case study.
Okay, thank you. Yeah, thanks for that introduction. Yeah, so thanks for having me, everybody. I'm going to be talking about a project I've been working on for several years, actually basically since I started in consulting. And it's going to be more methods-based. Unfortunately, I can't speak to the results specifically at this time because it's not quite in the public record yet. But yeah, we'll just go through this case study of determining anthropogenic versus geogenic arsenic, in particular in residential soils contaminated by a smelter impact. So I'll go over some of the key takeaways in case anyone's falling asleep. You can get those up front. We'll go through some smelter impacts to the environment and health, just a little bit of review on that, talk about the site geologic and mining background, our sampling program, the technical workflow, and then we'll end with some summary points. So some of the key takeaways for this talk are that all impacted sites are unique, and that is probably obvious, but it's particularly relevant at the site. So impacts can take on many different forms. The differentiation guides, are targeted closure expenditures and are aimed at the right problems. And then additionally, data quality gaps can lead to weak and/or subjective interpretations, and typical background soil determination guidance isn't quite sufficient for many sites that are very geochemically complex. And so we'll talk about a slightly different approach. And then the geochemical fingerprinting of complex contaminated sites can be aided by use of a more multifaceted technical approach that utilizes machine learning techniques. So just a brief introduction for those that are maybe less familiar. This is not the site, but it is nearby in Anaconda. This is the Anaconda smelter. And I really like this picture because I think it does a really good job of showing all of the potential impacts from metal smelting. And so here, here's the Anaconda smelter. You have this big plume of particulates that, depending on the type of smelting, can extend really long distances. In addition to that, the mining district itself has a lot of different types of pollutants. So you have a lot of different types of waste, from slag to tailings or whatever else you have on the property. And so as you can see, there are many types of impacts that you might get from toxic air pollutants, impacts to water quality, soils, you can get acid rain. And what's most particularly important to this particular study are the windblown effects. So the windblown effects from the particulates from the smelter, but then also other waste materials at the site. And then in addition to that, transport of those waste materials via storm events as well. The impacts are really controlled by several factors, and so those include the amount of emitted material. So how long was the smelter active, how much material was processed through the smelter, the particle size. So the particle size is dictated by the smelting process in particular. The stack height also plays a large role in the distance in which these plumes can reach. The wind regime is very important, right? Because most of the impact is going to be downwind of the smelter. And then also the topography plays a big role. And so because of that, every smelter site is very unique. So in the literature, there are lots of different studies done on smelter sites, and they're not all the same, for sure. There are similarities, but they're very unique. So in terms of human health risk, there are several different types of exposure mechanisms for smelter-related impacts. And so there's direct exposure and indirect exposure. So those include, air quality, soils, water, food products. Those contaminants can enter the ecosystems in several different ways. What's most pertinent to this study are the dust emitted from soils. And so when we get to the actual site, this is a residential area, and so the impacted soils are on people's properties, and so it's really the impact with that soil that is the contaminant pathway. And the main contaminant of concern for this study is arsenic, although we do have copper, lead, zinc, and all of these other metals. From a human health risk perspective, arsenic is the main contaminant of concern. So when you are doing a typical background study, you really need to be able to characterize all your sources. And so this is just a generalization of what those sources look like. So you have all of the sources from the mine district, in addition to, typical mining districts are adjacent to, where the material is being mined from. Those are often highly mineralized areas. And so you're going to get, soil and deposition from those geogenic, highly mineralized surrounding geologies. And then in addition to that, you're going to get other anthropogenic effects as well. So perhaps it's near a municipal waste incinerator. At this site, we have it's an old town, it's a historic town, so we have a lot of lead-based paints, wood preservatives, old fertilizers. These are also all contributing metals to the soils. And so we really need to be able to differentiate all these different sources to come up with a background value. So typical background soil determination workflows look like this. If you go to the guidance, it's pretty straightforward. So you do a big sampling and data collection effort. You go through a standard statistical approach. Then you do, look at the chemistry of the soils and do a comparison of all the different sources if you can. Look at the geology, lithology, grain sizes, which we'll talk about. And then at the base level, it kind of ends there. And then if you need, if the site is particularly complicated, you might need to go into a principal component analysis. And that's kind of where the guidance stops. But in this particular case, that really wasn't sufficient. And I've talked to several other people where they have felt the same way. Principal component analysis is a really good tool, but it also, for a lot of soil particular studies, it can be ineffective because a lot of soil data sets are really right skewed, they have a lot of outliers, and principal component analysis doesn't do well with that. Okay, so the site is located in Superior, Arizona, and so it's a mining town east of Phoenix. And so this is the residential town here with all of these kind of green, the green shaded areas are different parcels that we had sampled and throughout the site. And then directly to the west, bordering the town, is the mining district. And so the copper smelter was located here. And so major wind directions are kind of going to the northeast. And then we'll talk about the geology. But essentially, this is a population of about 2,500 people. Copper smelting operated for about 50 years in the mid-1900s. And the BHP assumed ownership of this mine site in 1996. They no longer own the site. It's owned by Resolution Copper, but they have assumed the responsibility of cleaning this up. And so they entered into a voluntary remediation program with the Arizona Department of Environmental Quality to clean up this site and enlisted us to help them with doing so. So in terms of the site geology, this is a map from the U.S. Geological Survey. So the study area is this, shaded blob. This is a very zoomed out picture. And essentially what you have on the north and the eastern side of the study area is this highly mineralized mountain front. So there's this eastern mountain front and a northern mountain front that has been subjected to lots of hydrothermal alteration, regional, extensional, and compressional forces creating all of these different faults. And so these faults acted as conduits for supergene and hypogene enrichment in the life cycle of this mountain range here. So this is our main source of heavy metals into this basin, which is a study area. And then to the south, we have influences from Picket Post Mountain, which is a felsic volcanic center that is younger than these mountains over here, but is contributing a lot of the soil to the southern area. So basically, as you can imagine, this basin here, this residential area, which is the site, sits, it basically abuts into this mountain front that is composed of different limestone units, volcanics, conglomerates. There's diorite porphyries, there's diabase, intrusions, shales, quartzites. So it's pretty messed up rock in here, and there's highly mineralized veins. And so both these veins and this mountain front are really rich in metals like arsenic, copper, lead, zinc, iron. And so these metals are the same metals that are what's going to be contributed from heavy mining impact in this area. And so we have this whole mine area here. There's a proximate boundary. We have tailings and slag piles down here in the historic copper site. And so all of this basin is being influenced by really similar chemistry. And so as you can imagine, teasing apart the sources is really difficult when your sources look very similar. And so you need to be able to identify several characteristics of each that are unique to be able to do this. And so, like I said, we have these several different sources, from the mountain front, this separate volcanic source, we have our mining-related materials, the residential towns and mixture, but then we also have our anthropogenic sources that we need to consider also and how those are impacting our analysis. So we need to be able to basically discern these different populations. And in addition to that, we need to understand, what are the common characteristics of smelter-impacted environments. And so these are 6 very common characteristics in the literature. If you go and look at, all the different types of smelter-impacted sites around the world, these are the most common things that you'll see. And so when we're going through this analysis, we're not only identifying the end members, but also trying to identify specific signatures that are relevant to the smelter impact to see how significant it is. So wind deposition, like I said, smelter deposition is always strongest in the downwind direction. Chemistry is very commonly associated with these particular metals: arsenic, copper, lead, zinc, iron, and sulfur. The bioavailability. So there is a decrease typically in arsenic, particularly in arsenic extractability, moving away from smelters and with depth. And so this is a really prominent feature that we can evaluate. And the reason that the depth profile, arsenic will decrease with depth fairly rapidly because the contamination is typically concentrated in the upper layers in more arid to semi-arid environments. Grain sizes. Smelter particulates are really small, and so you will generally see correlations between the chemistry and the grain size as well. And then particle morphology, which you can identify using SEM or electron probe techniques. So just kind of keep these things in the back of your mind. These are the things we're going to think about evaluating after we do our sampling and analysis program. So in terms of the sampling program, we collected surface and core samples across the site. So these are 5-foot core borings from the geogenic areas, the mine impacted areas in addition to the site, and then we also collected whole rock samples from the mine-related and geogenic sources as well to be able to identify those same signatures within the basin. Our main data gap is what actually came out of the smelter. Since our client no longer owns the site, we don't really have access to material on the site, and so this is a big data gap for us. How can we determine what the impact is from the smelter if we have no idea what came out of the smelter? Of course, we have some idea because we have historical information from other sites, but that is a data gap. And when the similarity between the smelter material and the geogenic material is so similar, that makes it really difficult. So we'll talk a little bit more about that. But basically, the types of data that we had available, we had 6-inch surface soil samples with chemistry, sequential extraction, SEM, and electron probe data. We have 5-foot drill cores. This is an example of one of the drill cores. Chemistry, grain size analysis, SEM, electron probe data, sequential extraction, and then geologic soil identification. And then we have our background reference data that Nick Tucci helped collect. He did a lot of the baseline work for this project. And then we have some mine-related material, but not all of our end members. And so when we're thinking about if the site is really characteristic of copper smelter impacted regions, again, we want to think back to what are the most common impacts from smelter deposition. And so, we went through, using Python and GIS packages, all of this different type of analysis, right, which is a whole other, 3 talks in itself. And we can talk more about this if anybody wants to. And these are just some example, figures with all of the data, and the results of this aren't important. But what we saw was that all of these different types of typical smelter impacts were not prevalent at the site. And so we really didn't have much to go off of saying like this site is very impacted because it was seemingly not very impacted at all. And there could be several reasons for that. And so, but I'll also say, we analyzed, 20, 25 elements. And so when you're trying to understand all of these different sources, different elements become better indicators for certain sources. So you're almost thinking in about 20-dimensional space. It's a lot to keep in your mind. This is a lot of data to try and, synthesize. And so what we did instead was switch to, move more towards a more machine learning type of technique. And so we used unsupervised and supervised machine learning techniques to try and understand this data. And so we started with principal component analysis and cluster analysis. This is just an example of a hierarchical tree that you get when you do a cluster analysis. So all of your samples will cluster in different groups. And that means something, which we'll talk about. And then we did briefly some supervised machine learning, which is basically you're training a model to make predictions for you. So essentially this typical background workflow becomes something that looks more like this. It's just a little bit more of an elaboration. These are typical, in the guidance documents, data you would collect, analysis that you would do. But these two pieces are really unique among the, these are used for more complicated sites, and they aren't really elaborated much in the guidance. They are a little bit more complex, and you really need to know how to use them. You can misuse them very easily, so I presume that's partially why they don't really talk about them. So I'm just going to focus on these two particular pieces of information in the coming slides. So this is an example output of one of our cluster trees. And so it's good to compare there's a lot of different methods for cluster analysis. The hierarchical cluster method is a really popular method. It's very flexible, easily interpretable. And so this tree, essentially, where'd my mouse go? Each of these groups are different subsets of samples. And so the closer they are together, the more related they are. And so this is just an example of one of our analyses where, we have one group over here, this kind of small group, that was most of our mining-related samples. It had off-site, our background samples, and it also had site data. So the reason we were doing this is we're trying to see which of our samples are most like our mining-related data that we had, because those are probably the impacted samples, and they need to be removed from our data set in order to establish a background data set. And then these other two groups were mostly background data and our site data. So these are considered our geogenic, groups, and these would be more our anthropogenic groups. However, we have background data within our anthropogenic group, and so what does that really mean? Again, you're still making subjective interpretations as to what that might mean. And so instead of, one method that you can use to kind of take the subjectivity out of the equation is to use more supervised machine learning techniques. And so this was an image published in a paper in 2023 that I really like. These authors implemented machine learning techniques at a lead zinc smelter site, and they were trying to basically model the changes in these metals with depth. And so essentially you can take all the data that we just talked about, all the chemistry, the geology, different types of data, and funnel it into a model that basically creates a prediction of your data and what are the most important pieces of data that control your constituent of concern. And so essentially we're taking all of this information that we gained from everything else we did and dumping it into this model to be able to figure out what's controlling arsenic. Are those controlling factors typically geogenic or anthropogenic? And what can we create basically a model to simulate arsenic behavior giving new data? And so this is just another example. I can't go into the results too much, but when we just look at all of our soil core data, essentially what we see is that this is a plot of score. So the higher the score, the more important the parameter is to predicting arsenic concentrations within the site. And so on the y-axis are the first 8 or 10 variables that were in the model. There were much more than this, and they don't even have to be numerical variables. But you can see, so the x-coordinate is the latitude, the y-coordinate is the longitude, and so these are obviously important because, like we said, there's a geologic interpretation for why those would be important. But also, the main metals that are important in controlling arsenic concentrations are aluminum, copper, barium, calcium. These are not typical mining-related elements. And so what we would have expected, in particular at this site, is that iron, copper, sulfur would have been the most important determining factors for predicting arsenic concentrations if arsenic was derived predominantly from anthropogenic sources. In this case, that's not what we found, and these are mostly geogenic metal sources. And so that kind of helped confirm and helped make our argument to the Department of Environmental Quality that this is really not a highly contaminated site. We did identify some contaminated samples that we removed from the data set, but we have a robust background data set to go off of, and they really liked seeing that. So I will skip to the last slide here. So essentially, just to summarize, some standard statistical approaches to background determinations are not always sufficient in complex sites. Incorporating machine learning, although it can be daunting, it's being used more and more in the literature and more in the industry. It's a really useful tool to establish, different sources within whatever type of data you have. And it can be applied to any site exhibiting anthropogenic impact, so you can better target closure options. And at this site, it really made the difference of, are we going to clean up the entire town, or are we going to clean up parts of the town, right? And we were able to show that there were only parts of the town that really needed to be cleaned up, and so that's a difference in between $10 million of cleanup or $300 million of cleanup. And so that was successful in that way. So, and this really applies to any type of data, soils, water quality, whatever type of data you have. And so I will stop there and take questions.
Thanks, Jenna. Yeah. Questions?
So as I understand it, you found that X and Y coordinates lat long is being the biggest determining factors mean that there is a geologic source. Would an aerial source also show X and Y?
It would, yeah.
Okay.
Yeah.
So how do you differentiate that?
Yeah, so we did a whole spatial statistical analysis of the site. So essentially what you see in typical smelter sites is you see a plume of metal deposition that sort of creates a circumference around the smelter site. We did not see that here, and so we did like a variogram analysis and spatial heat map analysis, and basically there's no statistically significant change in arsenic concentrations close to the smelter as being further away. But there is a difference in arsenic as you move away from the mountain front and to the south, where you're getting a further input from that volcanic material that's devoid of arsenic. So that's why those X and Y coordinates are most likely coming up as important indicators. And if I had seen that and not done everything else, I would have thought, okay, that seems like it's indicating more of an anthropogenic source. Yeah. But that's why all of that other stuff is equally as important to interpret the results.
Yeah, thank you. Can I have another question? Were lead isotope chemistry models considered for this? Do you know if they can distinguish aerial sources versus geologic sources?
Yes, definitely. They weren't considered for this because lead wasn't a constituent of primary concern.
Okay.
And so we didn't go down that path. But I have seen that in the literature as something that's useful. And so I had on that, flowchart isotopic analysis is kind of like a plus or minus, and it can be useful in a lot of situations for differentiating anthropogenic and geogenic sources, but it wasn't relevant for this.
Thank you.
Yeah.
Any more questions for Jenna? All right. Well, thanks, Jenna. We
Yeah.
appreciate you.
Thanks.